Hello there and welcome back to the Science Sleepy Minds. The lab hums under dim fluorescent lights. You stand before a screen, staring at a pattern that really shouldn't exist. A single particle was fired, just one, and yet the results suggest it somehow passed through two slits at once. The pattern isn't a splash or a dot, it's a ripple of impossibility. You blink. The lab hasn't exploded, and the laws of physics haven't apologized, but your grip on what is real is already beginning to fray at the edges. You're about to wade knee-deep into quantum mechanics, the realm where particles seem to vote on their own realities. You probably won't survive this with your common sense intact. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and local time in the comments. Let's see where and when you're listening from. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You trudge across the lab floor, the polished tile squeaking under your shoes, and peer again at the double-slit experiment set up in front of you. It looks simple enough. A photon emitter, a barrier with two narrow vertical slits, and a blank screen behind it. You fire a single photon, just one, and watch as the pattern builds one by one, not like tiny bullets hitting the screen, but like overlapping waves, forming an interference pattern. How? You think. This doesn't make sense. You're shooting one particle at a time. It shouldn't be interfering with anything. It should go through one slit or the other, right? But your results don't care what should happen. They just whisper back both slits, at once. This is the beginning of the quantum paradox, the feeling that reality, when examined too closely, collapses into riddles. The question, can particles really be in two places at once? The answer, not exactly, but also kind of. You sigh, press the button again, and fire another photon. The screen flickers. Another dot appears. Not randomly, but along a path that, once again, feeds the ripple, the interference. It's as if the photon split in two, went through both slits, and then recombined to decide where it should land. But here's where things get deliciously messy. When you watch the slits, literally just place a detector to observe which slit the photon passes through, the interference disappears. Just like that. The pattern becomes two neat piles behind the slits, like you'd expect from throwing grains of sand, as if the particle realized it was being watched and thought, oh crap, better act normal. This little game of hide-and-seek has baffled physicists since Thomas Young's first double-slit demonstration back in 1801. Although back then, it was about light as a wave. In 1905, Einstein complicates things by suggesting light is also made of particles, photons. Pick a lane, right? Nope. Even more confusingly, later versions of the experiment use electrons, actual matter particles, not light, and get the same wavy results. So, it's not just a weird thing about light. Reality, it seems, doesn't like being nailed down. Historians still argue whether this moment, the first realization that observation changes outcome, marks the true birth of quantum mechanics. It was certainly the first time the universe pulled back the curtain and said, oh, you thought I made sense. That's cute. But back to you. You lean in close. You need to know, how can a particle be in two places at once? The interference pattern suggests it's acting like a wave, spreading out, going through both slits simultaneously and interfering with itself. But you only fired one particle, and yet the pattern builds over time, unmistakably wavy. Here's a fringe thought. Don't worry, we'll have a lot of those. Some interpretations of quantum mechanics suggest the particle doesn't decide where it was until the moment it hits the screen. Until then, it's in a superposition, a math salad of probabilities. There's a spooky sense that the particle isn't anywhere until you look. Not here, not there, just possible. You step back. The screen's glow pulses gently like it's breathing. This isn't some ancient thought experiment. It's still happening right now. The most expensive labs in the world still run versions of this exact test, and they're still confused. One quirky twist. The pattern appears even if the slits are miles apart, and the particle is sent so slowly that it would be physically impossible for it to be in both places unless something truly weird is going on. And yet, the interference remains. You press the button again, another photon, another betrayal of logic. The particle is not in two places in the way a cat might be in both your sock drawer and under the couch. It's not literally split. Instead, its wave function, a mathematical expression of its possible states, stretches across both slits until you force it to choose, until you ask the universe a yes or no question, and the universe smirks and says, I'll think about it. If your brain's starting to get that fizzy, sleep-deprived feeling, congrats, you're getting it. One mainstream explanation, the Copenhagen interpretation, says particles exist in a cloud of probabilities until observed. Then, poof, the wave function collapses and the particle picks a state. But collapse is just a fancy word for we don't know what the hell just happened. There are competing explanations, of course. Historians still debate whether Niels Bohr's take on measurement ever really explained anything, or just delayed the panic. A fringe theory. That you split the universe every time you fire a particle. In the many worlds interpretation, the photon goes through both slits in separate universes. You're just stuck watching one of them. Infinite U's, infinite paths. Each time you make a decision, the universe spawns a new branch. Wild bedtime thoughts. You shiver a little, maybe from the lab's AC, maybe from the cosmic vertigo. You think back to that classic lab prank where someone smuggled in a chunk of uranium ore and left it next to the coffee pot. Haha, hilarious. Except now you're wondering what happens at the quantum level in your coffee. Do water molecules tunnel? Is there an entire version of you somewhere that didn't spill it on your shirt? Anyway, you're about to dig deeper into how this superposition thing really works. How particles can be here and not here at the same time. But first, let that double-slit image sit with you. One tiny particle, no interference. Two slits, still only one particle at a time, and somehow a pattern that only makes sense if it's in two places at once. Or maybe, and this is the truly spooky part, it's not that the particle is in two places, it's that you are in two places. You squint at the apparatus again, trying to make sense of it all, but it's not your eyes that are the problem, it's your expectations. You're still clinging to the idea that reality behaves itself, that things are either here or there, not smeared out in some unsettling both-and state. And yet, as you fire another photon, it politely ignores your instincts and lands exactly where the math says it will, in a pattern that suggests it somehow, impossibly, went through both slits. You're not alone in your confusion. In fact, welcome to the eternal party of puzzled physicists. If there were a mascot for the I Give Up Club of quantum mechanics, it would be the double-slit experiment. Streamers of probability, confetti made of wave functions, and an endless supply of skeptical stares. The whole thing starts out innocently enough. The double-slit experiment was first cooked up by Thomas Young in the early 19th century to prove that light was a wave. When you shine a beam of light through two parallel slits, the waves interfere with each other and produce bright and dark bands on a screen behind them, a textbook interference pattern. This was a win for the wave theory of light. Everyone clapped. But physics, like that one friend who always brings up controversial dinner topics, wasn't done stirring the pot. In the early 20th century, Einstein, yes, that Einstein, reintroduced the idea that light is made of discrete packets, photons, not continuous waves, but tiny particle-like chunks. So which is it? Particle or wave? You sigh because you already know the answer. Both, and also neither, and sometimes it depends on whether you're looking. Here's where the experiment gets sneakily terrifying. Once we had fancy gear capable of shooting one photon at a time, physicists decided to revisit Young's setup. They expected to see two tidy spots form, one behind each slit, as each particle picked a lane. But no. The interference pattern re-emerged slowly but unmistakably. Even though the photons weren't talking to each other, they were acting like a single wave split in two and interfering with itself. So being curious little reality probers, physicists decided to up the ante. Let's catch the photon in the act. Let's watch which slit it goes through. Sounds simple, right? Install a detector at each slit. See which one the photon goes through. Collect data, go home, write paper, get tenure. Except once the detectors were installed, the pattern vanished. Gone. No more interference. The moment we tried to observe which slit the photon passed through, the wave function collapsed. The particle picked a slit and stuck with it, like a child finally caught stealing cookies who suddenly decides honesty is the best policy. You lean back and wonder, was the photon always a particle that just seemed like a wave? Or is it the act of observing that forces it to become a particle? If you don't look, it behaves like a wave, rippling through both slits. But when you peek, It acts like a solid little point, with no wave-like behaviour at all. It's like that one co-worker who's perfectly productive, until someone asks what they're working on. Then suddenly it's spreadsheets and sighing. This is where the idea of wave-particle duality begins to haunt everything. Light behaves like a wave and a particle, depending on how you interact with it. Same goes for electrons, protons, even molecules. Scientists have done double-slit experiments with fullerenes, giant carbon molecules, and they still show interference patterns. Historians still argue whether this finding should have dismantled classical physics sooner, or if it was just one more nail in its increasingly quantum-shaped coffin. But the consensus is clear. The double-slit experiment isn't just a weird trick of light, it's a universal lawbreaker. Let's get a little weirder. You know, photons are massless, but electrons, those chunky little negative guys, have mass. They've got spin. They should behave like particles, right? Nope. Fire electrons through the slits one at a time, and guess what? The interference pattern comes back. The electron somehow goes through both slits and interferes with itself. This is where your sense of self-preservation starts to fray. Because if a single electron can do that, what's stopping you? A big old sack of electrons and atoms from being in two places at once. Don't worry, your body's too noisy. All the atoms around you are constantly bumping and jostling each other, collapsing wave functions faster than a toddler with a stack of Jenga blocks. That's decoherence, and we'll get to that later. For now, you're still staring at your particle behaving like a wave setup. A fringe theory pops into your mind, the pilot wave theory. This one says that particles always have defined positions, but they're guided by an invisible wave that determines how they behave, like a surfer who always rides the same wave, never straying but never quite in control either. Some physicists love this idea. Others, well, not so much. It adds hidden variables, and a lot of people think that's cheating, but admit it, it's kind of comforting, right? A world where things do have real paths, and we just can't see the underlying currents. A ghost map guiding every particle. You lean in, imagining the photon's journey. Maybe it doesn't split. Maybe it just rides a wave that splits, and the particle is along for the ride. Or maybe the particle is real and the wave is just math. Or maybe none of this is real and you're dreaming inside a cosmic simulation, and your observer forgot to install the logic patch this week. Hey, it wouldn't be the first time. One of your lab notes scribbled in the margin reads, "How does it know it's being watched?" That's the real kicker here, because your detectors don't even have to record anything. The very possibility of which path information being knowable is enough to collapse the interference. Even if you delete the data immediately, the pattern doesn't return. It's the act of measurement, or the potential for measurement, that changes reality. You close your eyes and try to picture it. A photon gliding through space, spreading out like a wave, flowing through two slits, cancelling itself in some places and reinforcing itself in others until you install a camera. Then it shrugs, shrinks, and picks a side. This isn't just spooky, it's deeply rude. Because now you can't trust reality to behave when you're not looking. It's not just if a tree falls in a forest anymore, it's if a photon goes through a slit and no one's watching. Did it go through both? The quantum answer, yes, and also number, and don't ask again. Another thought, could this dual existence explain why particles can be in two places at once? Maybe it's not literal, maybe it's mathematical. Superpositions aren't about a particle physically duplicating itself, they're about probabilities being real until they're not. You rub your temples, one photon, two slits, infinite migraines, and as the lab lights dim for the night, you can't shake the feeling that maybe the universe is watching you back. You wake up the next morning, not because you've solved anything, but because your brain, ever so slightly fried, decided to shut itself off sometime after midnight. The lab is quiet, the equipment is idle, but your thoughts are very much not. They're still orbiting the same irritating, impossible idea that a particle can be in two places at once, or at least act like it is. You pull up a stool and settle back in front of the screen. You've been through the double-slit experiment 100 times now, and it only gets worse. Because while the slits themselves feel like a riddle wrapped in a paradox, things get even more uncomfortable when you realise you can never really know both where a particle is and how it's moving. That's not just a philosophical statement, it's quantum law, and it's all thanks to a nervous-sounding German physicist named Werner Heisenberg. He was the one who decided with alarming confidence that the precision of what we can know about a particle is fundamentally limited. You can know where it is, or you can know how fast it's moving, but not both. Not fully, not ever. And that's not because of some flaw in your instruments, or because you're not trying hard enough. No, this is baked into the structure of reality itself. The more precisely you know one value, the fuzzier the other becomes. This, my friend, is the uncertainty principle. Heisenberg cooked up the idea in 1927, and the physics world promptly had a meltdown. Einstein hated it. God does not play dice, he said famously, but the math didn't care. The math shrugged and said, too bad. God's got a whole poker night going on down here. The uncertainty principle says, delta x times delta p greater than or equal to h bar divided by 2. Where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is the reduced Planck constant, which, let's be honest, sounds like something you'd find written in the corner of a cursed scroll. Translation: the more tightly you grip one of those variables, the more the other one squirms out of your hand. You lift your coffee, now lukewarm, and stare into the swirl of cream. That motion, it's deterministic. Classical physics says, if I know how fast the cream is spinning, I can tell where it's going. But if that swirl were a particle in the quantum realm, pick one, location or motion. And this isn't just a neat academic problem, it has consequences. Let's say you want to build a microscope powerful enough to see an electron. You'd need to use light with an incredibly tiny wavelength to resolve such a small object. But short wavelengths mean high-energy photons, and the moment your high-energy photon hits the electron, it nudges it, just enough to screw up your reading. The act of measuring position ruins your knowledge of momentum, and vice versa. You, dear lab rat, are stuck in a cosmic catch-22. The more you know, the less you know. Historians still argue whether Heisenberg's formulation was a limit on knowledge or a limit on reality itself. Is the electron just being shy, hiding its secrets from us? Or is there truly no real value there to find? Just a cloud of possibility waiting to collapse into something definite? Quirky side note? Heisenberg was once pulled over for speeding and, according to the joke, which may or may not be apocryphal, the officer says, "Do you know how fast you were going?" And Heisenberg replies, "No, but I know exactly where I am." Okay, it's physics humour. You're allowed to groan, just not too loud. The vacuum tubes are temperamental. You glance back at your photon. You know where it hit the screen. That's locked in. But what path did it take to get there? You can't know. If you'd tried to figure it out, the result would have been different. The path never existed in a classical sense. It was only one option in a frothy sea of maybes. Here's the whispering horror of quantum mechanics. We're not talking about uncertainty the way you're uncertain about whether you left the oven on. We're talking about fundamental indeterminacy. The world at this scale does not have the information until something forces it to choose. You clench your fist, resisting the urge to hurl your notes across the room. Classical physics told you that the universe was a clock. Mechanical, predictable, elegant. Quantum physics laughs and says, nah. It's more like a cat wearing socks on a waxed floor. And the deeper you go, the more the particles seem to resist definition. They're not really particles, not really waves. They're these probability distributions smeared across space-time, flickering like candlelight between what might be and what might never have been. One fringe interpretation tries to solve the problem by saying particles don't actually exist between measurements. They just aren't there. Like the photon isn't in a fuzzy state. It's in no state at all. The act of observing doesn't just change the state, it creates it. That's not just spooky, it's ontologically exhausting. You press the emitter again, another particle, another stubborn dot. You don't know where it came from, where it was going, or whether it even had a path. But now it's there, on the screen, insisting that you accept its existence. Another thought, how does this affect large-scale stuff? You know, apples, planets, you. Why aren't you smeared across your living room every time someone opens the door? Why does a baseball stay a baseball and not dissolve into a cloud of potential outcomes? The answer, decoherence. But don't get ahead of yourself. For now, just understand this. Quantum uncertainty is only noticeable at teeny-tiny scales. At your scale, the world looks crisp and coherent, not because it is, but because all the uncertainties are so tiny and tangled together that they cancel each other out like white noise. Still, the principle looms like a ceiling fan in a short room. You can ignore it most of the time, but when you jump too high, whack. And yet, there's a strange beauty in all this, a poetic fog that turns certainty into suggestion. It's like nature herself is saying, Relax. You don't need to know everything. Heisenberg didn't ruin physics. He made it real. He showed us that the universe isn't just a stage. It's a drama unfolding in real time, script unwritten, characters ad-libbing as they go. You sit with that idea for a long moment. Maybe that's why quantum physics keeps pulling at you like a half-remembered dream. Not because it makes sense, but because it refuses to. So you sip your cooling coffee and watch the next dot appear on the screen, certain of only one thing. You will never be certain again. The lab air is still, but your thoughts are anything but. You're now convinced that quantum mechanics is less a field of science and more a very polite, very confusing insult to common sense. And speaking of polite insults, it's time to talk about that cat. You know the one, Schrödinger's cat. You roll your chair toward the whiteboard, already crowded with squiggly diagrams, half-erased equations, and what might be a drawing of a cat wearing a lab coat. Probably your late-night attempt at making sense of it all. The cat, as you know, is both alive and dead until someone looks. But let's rewind. Erwin Schrödinger was not a fan of how quantum mechanics had started to lean into weird metaphysics. In fact, he came up with the cat not as an endorsement of quantum strangeness, but as a critique. A joke, really. A slightly morbid one. Here's the setup. You take a cat. This is theoretical. Place it in a sealed box. Inside the box, there's a radioactive atom with a 50-50 chance of decaying in a given time frame. If it decays, it triggers a Geiger counter, which then breaks a vial of poison. If the atom doesn't decay, the poison stays put, and Kitty goes on purring. Now, here's the quantum kicker. According to the Copenhagen interpretation, the one where particles exist in multiple states until measured, that atom is both decayed and not decayed, which means the poison is both released and not released, which means the cat is both alive and dead, until you open the box and observe it. And no, you can't shake the box and listen. That's cheating. You blink at the thought. Is the cat really in a superposition? Or is this a metaphor that got way out of hand? Historians still argue whether Schrödinger's cat was a thought experiment meant to highlight the absurdity of applying quantum rules to everyday objects, or whether it genuinely poked holes in the whole wave function collapse idea. Schrödinger himself leaned toward the former. He was a bit of a quantum realist, believing that something more deterministic had to be lurking beneath all this probability nonsense. Still, the cat refuses to die, or live, or pick one. So here you are, wondering how far this superposition idea really goes. You've accepted, reluctantly, that a single photon or electron might be in a superposition of paths, that its wave function might stretch out across multiple possible realities. But a cat? What does it even mean for something to be both alive and dead? You stare at the whiteboard cat, its little cartoon whiskers twitching in imagined defiance. The weird part is that the math works. Superposition isn't just some trippy idea, it's baked right into the Schrödinger equation, the fundamental tool of quantum physics. That equation describes how quantum states evolve over time, and unless you measure the system, unless you crack open the box, the wave function continues in a kind of spooky ballet, with every possibility still twirling. You step back and glance again at the apparatus. Could you build a Schrödinger's toaster, a Schrödinger's lunch order, a reality in which you both sent the email and forgot? In a fringe interpretation of quantum mechanics, the many minds theory, every possible mental state branches off like leaves from a tree. Not just the particle in superposition, but your thoughts in superposition. You open the box and in one branch you see the cat alive, in another dead. Your consciousness splits accordingly. If that feels like a migraine with a physics degree, congratulations, you're catching on. You're also starting to realize something else. Observation is a loaded word in quantum physics. It doesn't necessarily mean a person looking. It can mean any interaction with the environment that entangles the quantum system with something else. You don't need eyeballs to collapse a wave function. A Geiger counter will do, a dust particle, a photon, a cosmic shrug. But consciousness still creeps into the conversation. Some interpretations, yes, fringe ones, suggest that the observer's awareness plays a role, that it's not just about measurement, but about knowing. This leads into the territory of quantum mind theory, where the act of conscious awareness is thought to participate in reality's unfolding. Spoiler, most physicists avoid this like a sneeze in a clean room. Still, the thought lingers. Are you changing reality just by being aware of it? You glance at your own hands, particles, atoms, quantum soup, all the same stuff as the photon, And yet here you are, not smeared across probability states. Why? Decoherence. We'll come back to that. But for now, imagine the wave function not as a yes or no switch, but a tangled web of possibilities. Your poor cat is entangled with the fate of a single atom, and the moment that atom's state becomes known, even if you're not there to see it, boom, the cat's reality locks in. But here's where things veer into the gloriously ridiculous. Quantum eraser experiments have shown that you can erase witch path information after the particle has hit the screen and still recover the interference pattern. It's as if the universe is retroactively changing its mind about what happened, but you'll get there later. For now, the cat stays in its box, alive, dead, both, neither. You pace the lab floor, shoes echoing softly against the tile. There's something deeply poetic about this state of uncertainty. In a strange way, it mirrors real life. Decisions unmade, paths not taken, words you almost said. Maybe the quantum world isn't so different after all. Just a little more dramatic about it. One quirky historical footnote. Schrödinger wasn't only known for the cat. He also once attempted to create a unified field theory based on a fine field geometry, which went absolutely nowhere but sounded super impressive. He also vacationed with 2 girlfriends and a notebook full of quantum equations, because apparently even physicists can multitask emotionally. Back to the box. You imagine standing before it, hand on the lid, heart pounding. Do you open it? Do you want to know? Or is it better to let the cat stay in that strange in-between? That's the real bite of the paradox. Not that the cat might be both alive and dead, but that until you open the box, there's no real answer. Only a spectrum of possibility. Reality waiting to be decided. And it makes you wonder, how many boxes are you walking past every day? How many wave functions are you collapsing just by choosing one option over another? You exhale slowly, imagining the cat, furry, twitchy, possibly undead, stretching in that fog of unmeasured outcomes. You may never meet this hypothetical feline, but you're already tangled in the same web it is. Every moment your particles are tracing invisible lines through a maze of maybe. You don't need a box to find the paradox. You're already inside one. The whiteboard cat continues to stare at you, half smug, half doodle, all paradox. You swivel your chair away from it and stretch your arms toward the low ceiling, letting out the kind of sigh that only comes from spending several hours thinking about cats that are technically both fine and deceased. You need a break from feline metaphors. Thankfully, quantum mechanics has plenty of other flavorfully disorienting concepts to offer. Tonight's menu, superposition, the true heart of the 2 places at once mystery. You already brushed up against it when pondering that poor boxed cat. But now it's time to stare directly into the glowing, squirming center of it. Because superposition isn't just a quirky feature of quantum particles, it's the default mode of being at the quantum level. It works like this. Until a measurement is made, a quantum particle doesn't settle into a single state. Instead, it exists in a combination of all the possible states it could occupy. That's what we call a superposition. In math terms, it's represented as a sum of wave functions, a weighted mixture of options that only resolves into something specific when observed. You imagine a tiny electron sitting in a chair. Actually, it's sitting in every chair in the room. It's not teleporting. Don't get cocky. It's existing in all of them simultaneously, but only in the weird, fuzzy sense allowed by quantum physics. The moment you walk in and ask, "Hey, which chair are you in?" the electron picks one, and all the other possibilities vanish. Poof, gone. And no, the electron isn't trying to mess with you. It's just doing what particles do. This is its normal. You're the one with rigid expectations. This idea first really took off with Schrödinger's own wave equation. Yes, the same guy with the cat. His equation describes how a quantum state evolves over time, and crucially, how that state can be a sum of many possible outcomes. The mathematics says, here's every place the particle could be, but reality only picks one once you interfere. You feel your forehead furrow. What does it mean to exist in multiple states, you mutter out loud. No one answers. Your lab assistant left hours ago, probably to do something normal, like not question the nature of existence. Mainstream physicists agree that superposition isn't just a metaphor, it's real. A particle's wave function really does evolve as a combination of all possibilities. Electrons orbiting atoms, superpositions, photons travelling paths, superpositions, Neutrinos switching identities like cosmic shapeshifters. You guessed it, superpositions. Historians still argue whether Max Born's statistical interpretation of the wave function was a stroke of genius or a temporary patch on a deeper mystery. He suggested that the square of the wave function gives you the probability of finding a particle in a certain state. Not the particle's actual location or state, mind you, just where you might find it if you look. Born's take helped bridge the gap between the math and reality, but it left plenty of room for philosophical migraines. You rise and start pacing the lab again, like you're trying to outrun the concept, but it follows you like an invisible fog. Take your good friend, the electron. When unmeasured, its position is a fuzzy cloud, a probability distribution that spans space. It's not hiding, it's not waiting, it is the cloud. There's no real place it is until you poke it. Until then, every location it could be in contributes to its behaviour. This is how interference happens in the double-slit experiment. The particle doesn't split, it's in a superposition of going through both slits. That's why you get a wave pattern. When you observe which slit it goes through, you collapse that superposition into a single outcome, and the interference vanishes. Superposition is like choosing your dinner order by quantum roulette. Until you speak to the waiter, your meal is a mysterious combo of every item on the menu, tacos and sushi and lasagna. But as soon as you commit, reality serves just one. Hopefully not all three on one plate. Again, here's a fun fringe tidbit. Some physicists have experimented with placing larger objects into superposition, not just particles, but molecules. In 1999, a team managed to demonstrate interference patterns with buckyballs, giant carbon structures made up of 60 atoms. That's huge by quantum standards. Imagine a little molecular soccer ball being in multiple places at once. It happened. Since then, experiments have pushed the boundary further. There's even been work on putting small viruses or even tiny mechanical resonators into superposition. You could say researchers are playing a very gentle game of will it quantum, which makes you wonder, how far does it go? Could you hypothetically put yourself into a superposition? Not metaphorically, actually. You, smeared across a dozen outcomes, choosing multiple paths all at once. Cue the many worlds interpretation again, stage left. In that model, every time a quantum system branches, so does the universe. Instead of collapsing a wave function, reality just splits. The particle goes through the left slit in this universe and the right slit in another. Both outcomes exist, but in separate parallel realities. You're in one, but there are infinite copies of you in others, each watching their own version of the show. Fringe? Yes, but elegant in its own disturbing way. It removes the need for wave function collapse. Everything possible does happen, somewhere. You flop back into your chair and stare at the ceiling. So, I'm in superposition, but I can't feel it, you whisper. Exactly. Superpositions don't feel like anything. Because when you experience something, you've already decohered. Your state has been collapsed. You're no longer in all states, you're in this one. Still, it changes the way you think about reality, doesn't it? The idea that everything, every particle, every process, begins as a fuzzy bundle of maybes, only firming up into certainty when forced to? It makes you wonder if certainty is even real, or just a useful illusion, an afterimage of a collapsed possibility cloud. You glance over at your particle detector. It's off for now, but you know what it would show if you turned it on. Or rather, you know what it could show, because until you do, that particle might still be in every spot at once, hovering, waiting, but not really waiting, just being. One final thought before the clock ticks over and drags your sleep-deprived brain toward bed. Superposition isn't a glitch in the universe. It's the default state. It's not the particles that are weird. It's our expectations that they should choose a lane. And the moment we ask, the moment we demand an answer, then they do. But until then, they dance in every place and every way at once. You're not sure when it started feeling normal to think of reality as a fluid probability soup. But here you are, sipping lukewarm coffee and casually accepting that particles don't actually decide on a position until they're under observation. Comforting, in a deeply disturbing way. And just when you thought you had a loose grip on the idea of superposition, particles being in all possible states at once, along comes another layer of madness, entanglement. If superposition is quantum limbo, entanglement is quantum matchmaking, with all the drama and none of the consent. You pick up a notebook and sketch two tiny circles. Let's call them particle A and particle B. They're like the cosmic equivalent of twins separated at birth. You create them together in a way that their properties, say spin, are perfectly correlated. A might spin up, B spins down, or vice versa. But until you measure one, neither spin is decided. Now here's the kicker. Let's say you take particle B and send it across the lab, or across the country, or across the galaxy. You then measure particle A here on Earth, and it instantly chooses a spin. And in that same instant, no matter how far B has travelled, it will choose the opposite. Instantly. Not a bit faster than light. Not really, really quickly. Instantly. You squint, chewing on the end of your pen. This isn't just weird. It feels like cheating. Somehow, these particles communicate faster than anything should be able to. Einstein hated this. He called it spooky action at a distance. It sounded like something a kid would claim when caught breaking a window. I didn't do it, the particle did, from space. Yet, it's real, verified, replicated, unignorable. You remember the classic 1935 EPR paper, Einstein, Podolsky, and Rosen? Their argument was simple but fierce. If quantum mechanics allowed such bizarre correlations across distance, then either A, there's some hidden variable we don't know about, or B, reality isn't local. Einstein, ever the lover of neat causal chains, bet on A. But in the 1960s, John Bell came along with a now famous theorem. He showed that no local hidden variables could explain the results predicted, and later observed, in entanglement experiments. That left option B. The universe is non-local. Particles don't just communicate across space. They are linked, their states not separate, but part of a shared system. Historians still argue whether Bell's inequality test were the true death knell of classical realism, or just another blow to the slowly deflating balloon of common sense. You put down the pen. Your sketch of particle A and B now looks like two eyeballs staring at each other, judging you. Maybe they should. Entanglement isn't limited to spin. It can apply to polarization, momentum, energy, even position. Quantum teleportation uses it. Quantum encryption depends on it. And yet, no one, not a single person on Earth, can fully explain how it works. We just know it does. There's no signal between the particles, nothing travelling, and you can't use entanglement to send messages faster than light either. That's the cruel joke. Even though the outcome appears instantaneous, it's completely random. You can't control what result you get, only that once you get it, the other particle will match accordingly. Imagine calling your friend, flipping a coin, and instantly knowing their flip result will be the opposite of yours, even if they're on Mars. But you can't rig your coin. You can't send a message this way. It's correlation without causation, connection without communication. Still, the implications are massive. It suggests that space itself isn't what we think it is, that separation might be an illusion, that everything, at the deepest level, might still be connected. One fringe interpretation, you're getting good at spotting these, suggests that entanglement reveals a hidden layer of the universe, a kind of quantum field that spans everything, stitching particles together across space-time like invisible thread. The holographic principle, theories of emergent space, quantum gravity, they all try to wrangle this idea. You shiver slightly, not from cold, but from the sense that reality is playing a prank it's just too good at pulling off. You recall the 2015 loophole-free Bell tests. Multiple labs around the world closed all known gaps in the entanglement experiments, and still, quantum mechanics held. Local realism died that day with very little fanfare. You rub your temples and glance up at the ceiling tiles. Are you entangled with anything? Could you be? What about thoughts? Memories? Somewhere, in some parallel lab, is there another version of you drawing the same circles? And don't answer that, you're already spiraling. But the real fun comes when you combine superposition with entanglement. Now you don't just have particles in multiple states, they're in multiple states together. Their fates aren't just fuzzy, they're tangled up, inseparable. Measure one, and you collapse not just its possibilities, but the entire shared state. It's like tugging a thread in one dimension and watching it unravel in another. You can see why this isn't just a physics problem, it's a philosophical nightmare. What does it mean for two things to share a state? To be correlated in a way that ignores space? Are they truly two things? Or one thing pretending to be two? Another quirky thought. When you're born, some of your particles might already be entangled with ones scattered across the universe. You'll never find them. You'll never know. But when they shift, so do you. And it works in reverse. When you make a choice, if choice is even a thing, what subtle echoes ripple through that invisible network? This isn't just speculative nonsense, by the way. Entanglement has practical consequences. It's being harnessed right now in quantum computers, quantum key distribution, and cutting-edge encryption. Some startups are building networks that rely entirely on entanglement to transfer secure information. Unhackable, because any attempt to measure the system destroys the entanglement. That's quantum physics for you. The moment you snoop, it snitches. One final thought before you shut down for the night. We often think of particles as separate individual things, tiny, self-contained units, but entanglement tells a different story. It says that at the deepest level, individuality might be an illusion, that particles are not islands, they're threads in a web. Tug one, and the whole thing shivers. So maybe, just maybe, the universe isn't made of things. Maybe it's made of relations, and when you stop measuring, when you stop observing, maybe the world doesn't stop. Maybe it waits, entangled, suspended, still listening. You rest your forehead on the lab table, breathing slowly as if somehow that will steady the tornado of thoughts spinning behind your eyes. You're tangled up in a universe that doesn't behave, filled with particles that refuse to stay in one place, and now you've just accepted that two bits of matter can be cosmically braided together across entire galaxies. And you haven't even gotten to the really weird part yet. Because if entanglement makes space look like a suggestion, time is even less of a reliable friend in the quantum world. You glance at the digital clock glowing beside you. Hours, minutes, seconds, all tick forward like a faithful drumbeat. It feels objective, real. Time marches on, right? Seconds are seconds. The past is behind you, the future ahead. Except quantum physics is quietly laughing in the background, snickering like it just rewrote your calendar behind your back. You straighten up, blink, and start with something simple. Or rather, something deceptively simple. Cause and effect. You do something, and then something else happens. Flip a switch, the light turns on. Drop a cup, it breaks. One thing leads to another. This chain of events feels fundamental, axiomatic. But quantum particles don't necessarily agree. They behave in ways that suggest time might not be linear, or at least not as rigid as we like to pretend. Take the path integral formulation by Richard Feynman, that famously chill physicist who doodled quantum diagrams like they were Sunday cartoons. According to Feynman, a particle doesn't just travel from point A to point B. No, it takes every possible path between them, all at once. Straight lines, loops, zigzags, even ones that go backward in time. You raise an eyebrow. Wait, backward? Yes, the math allows for it. The particle's wave function includes paths that don't just take different spatial routes, they explore different temporal paths. Some interpretations of quantum mechanics treat time as another dimension like space. You don't move through time so much as exist across it, with quantum events smeared out in both directions. You fidget in your chair. This is the part where your sense of chronological stability starts to unravel. Because there are experiments, real ones, that suggest choices made in the present can affect events in the past. Let's talk Wheeler's delayed choice experiment. Strap in, John Archibald Wheeler, who you now suspect may have enjoyed confusing people for sport, took the classic double-slit setup and added a twist. What if you waited to decide how to measure a photon until after it had already passed the slits? Sounds innocent enough, right? You fire a photon, it goes through the apparatus. But just before it hits the detector, you choose. Will you measure which path it took, or will you measure interference, as if it went through both slits? And the photon responds accordingly, as if it knew what you were going to do, not just responds in a "this seems suspicious" kind of way, responds perfectly. If you choose to look at which path it took, the interference disappears. If you choose not to look, interference returns, even though your choice happens after the photon passed the slits. You rub your eyes. This can't be real, but it is. Verified, repeated, peer-reviewed. The implications, the future seems to influence the past. Historians still argue whether Wheeler meant to break causality, or just bend it slightly for dramatic effect. But the results are clear. Quantum particles don't care about your tidy timeline. They're playing a different game. You scribble a note on a napkin. Does the universe have a memory? And then? Or does it just make things up after the fact? Let that thought sit with you for a second. Maybe the universe doesn't decide what happened until everything's been measured, until all the context is in. It's like watching a crime drama where the ending changes depending on which character you sympathize with, retroactively, as if the events themselves were fluid. One fringe interpretation suggests this means reality is retrocausal, that effects can influence causes, not just the other way around. It's not time travel in the traditional sense, no DeLorean, no flux capacitor, but it's worse, it's subtle, it's structural. It means that what you do now could shape what was already true. You look over at your screen again, where another photon has dutifully hit its mark. Did your choice to turn on the detector affect what that photon was, even before it got there? You could almost swear the lab feels smaller now, like the walls are creeping in, not physically, but philosophically. Time, which once felt like the comforting scaffolding of your reality, is starting to feel optional, or at least negotiable. Another eerie quantum fact: time doesn't appear in the fundamental equations the way you might expect. The Schrödinger equation describes how quantum states evolve, but it doesn't treat time as a standalone backdrop, it's just a parameter, another slider on the cosmic mixer. Some physicists trying to unify quantum mechanics with general relativity propose that time is emergent, a product of entanglement, observation, and perspective. In other words, time might not exist at the most fundamental level. It's something that appears once particles start interacting, like foam on the surface of a wave or traffic during rush hour. It feels real, but it's a product of deeper chaos. You frown. Does this mean the past doesn't exist? That the future is already here? That the moment you're in now is just a convenient illusion built by your brain? There's a comforting mainstream view that says no, relax. Quantum mechanics is probabilistic, not conspiratorial. The delayed choice experiment doesn't rewrite the past. It just reveals that the past was never concrete in the first place. The particle didn't have a fixed path, it had potential paths, and your later choice collapses that ambiguity. But that's not more comforting, really, because now you're left with a universe where cause and effect are not so much a domino chain, but a dance, a tangled waltz of options with steps chosen after the music ends. You check your watch, just to be ironic. Time, after all, is what your watch measures, but not necessarily what your particles experience. And that's the secret, isn't it? At your scale, humans, coffee, to-do lists, everything looks clean, linear, predictable. But deep below, at the scale of atoms and photons, the universe isn't marching forward. It's shifting sideways, looping, waiting. One last thought before you wrap up for the night, and it's a doozy. If time isn't real, at least not in the way you think, then neither is before and after. And if observation can affect the past, then maybe everything that's ever happened is still editable. Maybe every moment is like a page in a quantum scrapbook, fuzzy, flexible, and always just one measurement away from being rewritten. So you sit there in your lab, surrounded by blinking machines and silent clocks, wondering, what else have you already changed? Without knowing. You stare blankly at the screensaver flickering across your monitor. Digital stars bouncing softly against the edge of a void. It's meant to simulate the universe, but you're starting to think it's actually simulating you, pinging around in an expanding field of uncertainty. Particles aren't behaving. Time might not even exist. So naturally, your next step is to question the nature of reality itself. You stand, crack your back, and wander to the whiteboard again. Still haunted by Schrödinger's smug cartoon cat in the corner, but this time you're not drawing. You're just staring at everything. The table, the chair, your own hand, all of it made from particles. All of those particles obeying quantum rules that allow them to be in multiple places at once, to entangle across light years, to ignore time like it's a minor suggestion. So what does that mean for the world you live in? Here's where it gets uncomfortably theoretical, danger nap territory. You're entering the realm of the many worlds interpretation. This idea, most closely associated with physicist Hugh Everett III, basically says this: the wave function never collapses. Ever. Instead, every time a quantum system chooses an outcome, say, a photon goes through the left slit or the right slit, it doesn't pick. It does both, and the universe just splits. That's right. According to many worlds, all outcomes happen, all measurements are real. They just happen in separate branching versions of reality. So in one universe, you finished your thesis. In another, you became a llama farmer. In another, you're still debating whether to order Thai or pizza. Each version just as real. Each one a full-fledged universe with its own consistent history. And every quantum event, every wiggling electron, every decaying atom is a fork in the road that branches reality further. You sit down slowly because your knees feel weirdly wobbly now. It's not just metaphor, it's math. In the Everettian model, the universal wave function evolves deterministically, according to Schrödinger's equation. No randomness, no collapse, just branching. At each quantum event, the observer becomes entangled with the observed, and when a measurement is made, the observer splits too. So when you measure the spin of an entangled particle, you don't cause it to pick one spin, you cause two U's to branch, one that sees spin up, another that sees spin down. It's you, and also not you. You're used to the idea of being one self, one consciousness. But in many worlds, you're constantly fracturing, endlessly replicated across a growing multiverse. The you, reading this, just one thin slice of an ever-expanding stack. It sounds ridiculous, right? Like sci-fi wish fulfillment with a PhD. But many worlds has serious support among physicists, especially those who dislike the idea of wave function collapse being some magical, unobservable event. If you take quantum mechanics at face value, with no special exceptions for measurement, this is what you get. Infinite realities. No collapse, just splitting. Historians still argue whether Everett's paper was ahead of its time, or just an audacious mess that got rescued by later physicists. He published it in 1957, and for decades it was mostly ignored, except by a few visionaries who saw in it not madness, but a chilling kind of clarity. And here's the most unsettling part. Many worlds is testably equivalent to other interpretations. It makes all the same predictions as Copenhagen, pilot wave theory, and others. You can't tell, just by running an experiment, which interpretation is correct. All of them match the data, but they paint very different pictures of reality. You stare at your reflection in the screen's dark glass. Is that you, or just one version? You think about decisions you didn't make, paths you didn't take, and somewhere, if many worlds is right, you did. All of them. There's a universe where you skipped this lab session and got caught in the rain, another where you accidentally discovered cold fusion in the break room microwave, another where you're a goat, for some reason. But it's not just about fantasy. This isn't about living your best life somewhere else. It's about the idea that reality isn't singular, that the particle doesn't decide. The universe does, by dividing itself. One quirky thought: if all outcomes happen and you keep branching infinitely, does that mean free will doesn't exist? Or does it mean free will always exists because every possible choice is made somewhere? It's like being stuck in a choose-your-own-adventure book where you read every ending simultaneously, whether you want to or not. You shudder slightly. There's also a practical headache. If universes are constantly splitting, where are they all stored? Are we creating energy by spawning new timelines? Is there a cosmic file cabinet somewhere overstuffed with versions of you who made slightly worse jokes? Most physicists sidestep these questions. After all, many worlds doesn't require extra energy. It's just a consequence of taking the math seriously. Still, the metaphysical baggage is substantial. You pace the lab again, like that'll help you outrun infinity. Maybe it's not about splitting in a literal BAM, a new universe sense. Maybe it's about decoherence. When a quantum system interacts with its environment, the superposition gets spread out. The different branches no longer interfere. They evolve independently, as if separate. So it's not so much that the universe splits as that it diverges, like two radio stations playing at once until they slowly drift out of tune, until you're left only hearing one, and yet the others are still broadcasting. Somewhere. You imagine your particle, somewhere in its fuzzy state, choosing a direction. But instead of collapsing, it keeps both. Just not here. Somewhere close, but unreachable. That's the real sting of many worlds. You don't get to visit the other branches. There's no interdimensional tourism, no sneaking a peek at alternate yos. Once you decohere, you're locked into your timeline. The others exist, but they're forever orthogonal. You can't hear them, touch them, warn them about that time you licked a frozen pipe in 3rd grade, and they can't warn you. One last unsettling whisper before the coffee wears off. If quantum events happen constantly, and they do, then universes are branching constantly, right now, as you blink, as your neurons fire, as your thoughts shift. You're standing in a cloud of possible futures collapsing into just one. But the others, they're still out there, still you. And somewhere out there, another version of you just realized the exact same thing. The lights hum softly above your head, and you're vaguely aware of your own breathing, measured, shallow, like your body's trying to steady you before your mind decides to jump into another rabbit hole. You've walked through superposition, dabbled in entanglement, tiptoed across alternate realities, and yet, somehow, you're still clinging to one last scrap of comfort. The idea that you're just a bystander in all this, that reality will unfold the same whether or not you're paying attention. Bad news, you're not off the hook. Because tonight, you're facing the most uncomfortable idea of all. When you look, it's already different. It's not just that quantum particles behave differently when observed. It's that the very act of observation changes the outcome. You rub your temples. This sounds like old news, right? After all, you've been through the double-slit experiment. You've seen how trying to determine which slit the photon goes through collapses its wave function, eliminating the interference pattern. But tonight, you're going deeper, into the idea that observation doesn't just reveal information, it creates it. You set up the classic experiment again, double slits, single photons, and just for fun, you install a fancy witch path detector behind one of the slits. High-end stuff, ultra-sensitive. You start firing photons one at a time. They land in tidy little clusters, no interference pattern. The act of measuring which slit the photon travels through collapses the wave function. It chooses a path. It obeys. It gets boring. Then you think, what if I leave the setup the same but turn off the detector? Just power it down. Don't change its position or the photon's path. Just stop collecting data. Suddenly the interference pattern returns. The photon somehow knows whether the information is being recorded. It doesn't care about the wires, the lenses, the circuitry. It only cares about whether witch path knowledge is, even in theory, available. Which means it isn't physical measurement that causes collapse. It's information. That's the moment your stomach turns slightly. Because now reality isn't just altered by interactions, it's altered by potential knowledge. The mere possibility of knowing seems to change the outcome. Historians still argue whether this is a measurement problem, a metaphysical loophole, or simply an artifact of how we define observation in quantum mechanics. But the results keep coming back the same. What you choose to know, or not know, shapes the event retroactively. It makes you think of something Niels Bohr once said, in his usual enigmatic fashion. No phenomenon is a phenomenon until it is an observed phenomenon. Chew on that. Not, you can't know about a thing until you observe it. But the thing itself does not happen until it is observed. You sit back down and scroll through some old lab logs. There it is again. Inexplicable result clusters that only made sense once the observer effect was factored in. You hadn't noticed it before. Or maybe, until now, you didn't want to. This isn't about the detector messing up the particle's trajectory. It's about reality reorganizing itself around what's measurable, around what's meaningful. Here's a quirky historical tidbit. During the Manhattan Project, some scientists became so obsessed with quantum measurement theory that they joked the atomic bomb would only detonate if someone was looking at it. Grim humor, but also strangely consistent with quantum logic. You run simulations, you read papers, you get sucked into forums full of people with usernames like Heisenberg42 and WavyGravy88. They all seem to be chasing the same question. What counts as an observation? Does it have to be human? Is a camera enough? A rock? Can a particle observe another particle? The mainstream answer is slippery. Measurement isn't clearly defined in quantum mechanics. It's not about eyes or consciousness. It's about interaction. Once a quantum system interacts with another in a way that creates entanglement and decoherence, the wave function collapses, or appears to. But this just moves the problem. Now the question is, at what point does an interaction become irreversible? When does the blur of possibilities harden into fact? You glance back at your latest trial runs. Some show an eerie pattern, others show clean data. The only variable that changed, whether the system could be observed, not was. You take a sip of coffee, now cold. You grimace, not just because it tastes like quantum sludge, but because you're beginning to realize the implications. If particles behave differently based on whether their path can be known, then reality is conditional, not fixed, not absolute. It adapts, It's like the universe is doing improv. You set the stage, you give it cues, and it responds. This makes you wonder, how much of the world around you is real in the sense you assume it is? Your desk, your keys, the sandwich you definitely meant to eat hours ago? Are these objects collapsed wave functions? Or are they waiting, hiding in superpositions, becoming real only as you engage with them? In quantum terms, the world isn't made of things, it's made of events, and an event isn't real until it's part of a measurable outcome, until it enters the classical world of results and records and evidence. You remember reading about an experiment where scientists entangled particles and delayed the measurement long after they had travelled and interacted, and yet the measurement still affected the result after the fact, as if the past itself had been rewritten to be consistent with what was eventually known. You start to feel it again, the creeping suspicion that you're not just watching quantum mechanics unfold, you're participating in it. One fringe theory, lovingly controversial, posits that consciousness might be the final link in this chain, that the universe doesn't truly crystallize into existence until it is experienced. It's called the observer-dependent reality hypothesis, wildly unpopular among most physicists, but still whispered about in late-night conferences and philosophical journals. The idea: conscious observers don't just observe outcomes, they select them. Not with willpower, but by being the end of the measurement chain. By collapsing possibilities into the singular version that registers as your experience. You try not to spiral. Maybe it's just math. Maybe wave functions collapse when you drop your detector into the data analysis software, not when you blink at the screen. But even if you stick to the most grounded interpretations, the unsettling truth remains. Looking changes things, and not just in the fluffy, metaphorical, your perception shapes your reality kind of way. In a hard, testable, repeatedly verified kind of way. You look, and the world changes. You don't look, and it stays incomplete. So now you wonder, if observation defines reality, then what about everything you haven't looked at? What's waiting behind every unobserved corner? And what might change the moment you turn your head? You push back from your desk, the chair creaking beneath you, and stare up at the ceiling tiles like maybe, just maybe, they'll offer answers. You've spent hours tangled in the quantum jungle, where observation changes outcomes, particles flirt with multiple realities, and time just kind of does its own thing. You've tried to keep one foot in the familiar world of logic and reason, but it's slipping. Because now we're going to talk about the thing that really breaks your brain. Wave goodbye to logic, because quantum particles don't behave like particles, and they don't really behave like waves either. They behave like both, or neither. Or something new entirely that just borrows the costumes of particles and waves depending on who's watching. Take light. Classical physics used to think it was a wave. Easy. Thomas Young's double-slit experiment in the early 1800s confirmed it. Those clean, crisp interference patterns could only come from a wave passing through two slits and interfering with itself. Then, bam, Einstein comes along in 1905 with the photoelectric effect and says, actually, light is made of particles, photons. That's how he got his Nobel Prize, by the way. Not for relativity, for telling everyone light comes in packets. So, is light a wave? Or is it a particle? Yes, and no, and maybe. And also, it depends on what you ask it to be. This is wave-particle duality, one of the oldest and most stubborn paradoxes in quantum mechanics. Light behaves like a wave in some experiments, interference, diffraction, polarization. But in others, it behaves like a particle, bouncing off surfaces, ejecting electrons from metal plates, being counted one at a time in photon detectors. Electrons? Same story. You'd think they'd behave like little charged balls, right? Nope, they show interference patterns too. Even full molecules, like buckyballs, those weird soccer ball-shaped carbon structures, can act like waves. Until you try to pin them down, then poof, they collapse into particles. You set up the math to predict the next outcome, and you find yourself using the wave function, which is, annoyingly, a wave. It's not a wave like a sound wave or a ripple in water. It's a wave of probability amplitude, a fancy way of saying what might happen but isn't happening yet. That wave function evolves over time, it spreads out, it interferes with itself, it builds those lovely patterns. But the moment you measure, that beautiful wavy soup turns into a single number, a single result, one photon, one detection, one click in the box, is like watching a firework explode in perfect symmetry and then finding only one spark in your hand. You frown. Okay, you mutter. Maybe I can live with the mystery. Maybe particles just wear different hats. But no, it's worse than that. Because the quantum world doesn't just defy logic, it rewrites it. In classical logic, something is either true or false. It's either A or not A. There's no halfway. Quantum logic says, well, what if A and not A both apply until you measure? Superposition allows contradictory states to coexist. Schrödinger's cat isn't metaphorically dead and alive, it's literally both in the math. You scowl at your laptop and open a textbook like it's going to apologize. It doesn't. It gives you a wave equation. And then there's the fact that when you run an experiment, say measuring the position of a particle, you can't then immediately know its momentum. Not just practically, fundamentally. You've altered the system by asking it a question, like interrogating someone so hard they forget their own birthday. This is the complementarity principle championed by Niels Bohr. It says that some properties are mutually exclusive, not because the particle is shy, but because the universe has rules about what it will reveal to you at the same time. Measure one thing, and you lose information about the other. It's like asking your GPS for directions and then having it forget where you are. Historians still argue whether Bohr's complementarity was a brilliant philosophical insight or just a polite way of saying, please stop asking. But the universe doesn't care what you want to know, it plays coy, and every time you demand answers, it gives you riddles wrapped in math. And then, there's quantum interference. You set up two paths for a particle, one left, one right. If both paths are open and indistinguishable, the wave function from each path interferes with the other, creating that lovely ripple pattern on your detector. Peaks where waves reinforce, valleys where they cancel out. But if you even try to gain which path information, if you so much as breathe in the direction of knowing, it's over. The interference collapses, the patterns vanish, the particle becomes just a particle again. You sip your coffee and make a bitter face. This cup is real, the caffeine is real. But now you're starting to question whether the atoms in the coffee are in wave states you've accidentally collapsed just by tasting them. Even more frustrating, quantum systems are completely predictable in how unpredictable they are. The probabilities work, the math works. Every test, every experiment, every measurement falls neatly into line with quantum predictions. It's almost perfect. It's also completely absurd. One fringe interpretation, the quantum Bayesian approach, suggests that the wave function doesn't represent something real at all. It's just a tool for updating your beliefs based on new information. The particle is never in a superposition, they say. That's just your best guess before you check. But then you run into that old problem again. The math only works if you treat the wave function as real. If you start thinking of it as just a human error margin, the theory falls apart. It's like trying to play poker with imaginary cards and still losing money. So here's the truth. There's no neat line between particle and wave. No secret handshake that lets you decode reality cleanly. Quantum objects are neither one nor the other. They are quantum things, obeying quantum rules, and the labels we try to force onto them, wave, particle, thing, logic, object, don't quite fit. It's like trying to pour soup into a mailbox. You sit in the dim light of the lab, silence pressing down gently, and you wonder what the point of it all is. If everything at the smallest scale is fuzzy, shifting, ambiguous, how does anything solid emerge? How do you get a chair out of a smear of probabilities? A cat? A brain? You have a guess. But first, you'll need to understand what happens when quantum weirdness meets the noisy classical world. Because something does force the universe to stop waving and start deciding. It's coming. It's called decoherence. You know that feeling when you're staring at static on a TV and your brain starts trying to see patterns that aren't there? A face, a shape, a message from another dimension. That's a little like trying to make sense of quantum mechanics from a classical perspective. You're trained to look for solid answers. Particles here, waves there, cause, effect. But the quantum world is static, buzzing with possibilities, and your brain just can't stand it, so it starts stitching meaning together. That stitching? That's what brings us to decoherence, the great silencer of quantum weirdness. You're still in the lab. The coffee's gone, the overhead lights are flickering in that charming budget cut sort of way, and your notes are starting to look like the conspiracy board from a true crime documentary. You flip to a clean page and write one word at the top. Why don't I float through walls? Because if quantum particles can tunnel, exist in multiple places, and interfere with themselves, why doesn't your entire body behave like that? Why aren't you a walking probability wave? Why don't you exist in a shimmering cloud of alternate states? Here's the mainstream answer. You do. Or rather, the particles that make up your body do. But they decohere almost instantly. In a pure quantum system, something small, clean and isolated, superpositions are preserved. You get interference, entanglement, all the spooky, slippery behavior you've come to expect. But once a quantum system interacts with its environment, air molecules, radiation, your lunch, anything, it starts to lose its delicate coherence. The environment measures it in a way, even if no conscious observer is present. It's not a human gaze that collapses the wave function. It's interaction. That's decoherence. It's the reason quantum behaviors don't scale up cleanly to the classical world. You imagine a poor little electron trying to be in two places at once, drifting happily through its own superposition, until it collides with a dust particle, or a photon, or another electron. Suddenly it becomes part of a larger system. Its superposition bleeds into the environment, and the neat wave function collapses into a messy, classical outcome. It's not that the quantum behavior stops, it just gets distributed, spread out across so many particles and interactions that it becomes impossible to track. The information is still there, buried in the correlations between the system and the environment, but it's hopelessly entangled, irretrievable. It's like trying to unscramble an egg with tweezers. Historians still argue whether decoherence solves the measurement problem or just sweeps it under the cosmic rug. Does decoherence explain why a single outcome is observed? Or does it just explain how possibilities get filtered into apparent classical behavior? Regardless, decoherence is fast. For macroscopic objects, say, a speck of dust, it takes less than a trillionth of a second for coherence to vanish. That's why you don't see dust bunnies in multiple locations, why your cat, alive, dead, or judgmental, doesn't smear across dimensions. And you? The human body, composed of quadrillions of interacting particles, is a decoherence factory. Every breath, every twitch, every neuron fires off entanglements with the environment like a quantum disco ball. You don't get to be in multiple places at once, not because you can't, but because your system is too noisy. The superpositions are still there deep down, but the signal has drowned in the noise. You close your eyes and picture it, each particle in your body dancing a delicate quantum waltz, until decoherence grabs it by the shoulders and yells, "Okay, pick a side." Another fringy twist. Some theorists suggest that decoherence doesn't just explain why we see one outcome. It might be responsible for why the universe has classical outcomes at all. That the classical world is just the illusion created by a massive quantum system decohering constantly, too quickly for weirdness to build up. And if you rewind the clock, way back, things get even more interesting. Early in the universe, conditions were much more uniform. Fewer interactions, simpler systems, superposition and entanglement could stretch across vast distances. It's possible, some argue, that decoherence itself played a central role in how reality crystallized into something we could later call space and time. You scribble something half-legible. Did decoherence make the Big Bang classical? Then you stare at the words and immediately regret thinking them. You need a break, a breath. So you look out the lab window. The streetlights cast soft glows across the pavement, and a lone raccoon shuffles past. Looking like it too, has just read about quantum measurement. Here's a quirky fact to settle your brain. In 2011, researchers managed to place a tiny drum, big enough to be seen with the naked eye, into a superposition of vibrating and not vibrating. That's a macroscopic object, behaving quantumly, but they had to isolate it from everything, cool it to near absolute zero, shield it from stray light, keep it away from the breath of curious raccoons, and even then, the coherence lasted a fraction of a second. That's how fragile quantum behavior is at scale. One stray interaction, and it's gone. Still, it proves something. Quantum mechanics doesn't stop applying just because something's big. It's not a size thing, it's a context thing. If you could perfectly isolate a baseball or a brain, it too would exhibit quantum behavior in principle. The reason classical logic holds up in your daily life is not because it's truer, it's just more stable, like a fog that only clears when you zoom in. Up close, particles blur, systems shimmer, reality pulses with options. But step back. It all hardens into chairs, cats, coffee mugs. Solid, predictable, familiar. But now you know better. You know that under the surface of every classical object is a roiling sea of quantum probability, that every thing is just a temporarily coherent pattern, stitched together by trillions of decohering events. You are a statistical miracle. You're walking through a world that should be weird, but got washed clean by interaction. So the next time you place your phone on the table and expect it to stay put, remember this. It's not logic that keeps it there. It's decoherence. A fragile consensus between trillions of entangled particles and the environment screaming, "Just act normal!" And for now, that's enough. You blink a few times trying to refocus your eyes. There's a particular kind of mental exhaustion that only comes from spending several hours whispering to atoms in your mind, asking them to kindly explain themselves. They don't. They just keep tunneling through the walls of your logic like it's not even there. And speaking of walls, tonight's quantum trick is one of the weirdest. Quantum tunneling, how particles break the rules. You've been taught since childhood that solid things can't pass through other solid things. That's why keys go into locks, not walls. Why you don't walk through doors without opening them first. That's classical intuition, reinforced by a lifetime of not falling through floors. But quantum particles didn't get the memo. In the quantum world, there's a non-zero probability that a particle can pass through a barrier it shouldn't be able to cross. No bulldozing, no blasting, just appearing on the other side, like it slipped through reality's DMs. Let's walk through this with something simple. Imagine a tiny particle, like an electron, approaching a wall. Not a literal brick wall, but a potential energy barrier. Think of it like a hill the particle would have to climb to get over. Now, if the particle doesn't have enough energy to get over the hill, classical physics says, tough luck, turn around, try again later, or just stay and sulk in front of the hill forever. Quantum mechanics says, hold my uncertainty principle. Even if the particle doesn't have enough energy to climb over the hill, there's a small chance, a real, measurable chance, that it will just appear on the other side. It didn't jump, it didn't burrow, it tunneled. Why? Because particles aren't little marbles, they're also waves, and a wave doesn't just stop at a barrier. It fades, it stretches, it leaks. The wave function describing the particle can extend through the barrier, decaying as it goes. And if the barrier is thin enough, and the wave function doesn't completely disappear inside it, there's a chance the particle will emerge intact on the other side. You lean back in your chair and mutter, "That's cheating." The universe doesn't reply. You've actually seen this in action, even if you didn't know it. Quantum tunneling is the reason stars shine. Inside the sun, hydrogen atoms are fusing into helium. But to do that, they have to overcome the strong electromagnetic repulsion between positively charged protons. Classically, the sun's temperature isn't quite high enough for that to happen efficiently. Protons shouldn't get close enough to fuse, but quantum tunneling lets them bypass the classical limit. Historians still argue whether quantum tunneling was first understood in nuclear decay or electronics, but one of the earliest clear applications was in radioactive alpha decay. A nucleus that shouldn't be able to eject an alpha particle, because it's trapped in a potential well, still does. The alpha particle tunnels through the barrier and flies off. Goodbye. You check your phone, probably assembled using components that only exist because of tunneling. Modern electronics, especially semiconductors and transistors, rely on this behavior to function. The entire computer you're using, from its processor to its memory, plays host to tunneling events. There's even a quirky trick in biology. Some enzymes appear to rely on quantum tunneling to speed up chemical reactions. Protons and electrons tunnel from one molecule to another, allowing reactions to happen far faster than they would if the particles had to physically climb the energy barrier. So yes, particles are rule breakers, but in a predictable way. You can calculate tunneling probabilities. You can build technologies around them. They're rebels with very precise causes. Still, the philosophical implications are not subtle. You walk over to your lab's lead-lined barrier, solid, heavy, impenetrable. But somewhere, a quantum particle is shrugging and deciding it might just sneak through anyway. You ask yourself, if a particle can tunnel through a wall, why can't I? And the answer, as usual, is decoherence. You're too big, too entangled. Your wave function doesn't stay coherent long enough to allow that kind of behavior. For you to tunnel through a wall, every single atom in your body would have to simultaneously align in the same quantum way and then reappear, fully intact on the other side. The odds of that happening? about the same as finding Schrödinger's cat alive, dead, and holding a latte with your name on it. But in theory, not zero, there's a fringe story, probably apocryphal, about a physicist calculating the odds of a human quantum tunneling through a wall. The result was something like once in a time span longer than the current age of the universe multiplied by the number of atoms in existence. So technically possible. Practically, keep using doors. Still, tunneling leaves a fingerprint, you can't unsee it. You think of a simple image, a ball rolling toward a hill. If it doesn't have enough speed, it stops, slides back. That's classical physics. In the quantum version, the ball might vanish as it hits the hill and reappear on the other side, continuing on as if nothing happened. You tap your pen nervously. This is how scanning tunneling microscopes STMS work. They bring a sharp metal tip incredibly close to a surface, so close that electrons can tunnel across the tiny gap. Measuring that current lets you see surfaces at the atomic level. Your eyes can't do that, but tunneling can. And quantum tunneling may even play a role in the process of mutation. Some physicists speculate that protons in DNA can tunnel from one position to another, subtly altering the genetic code. The implications? Evolution might be in part quantum-powered. That twist in the helix, that butterfly gene, that eye colour, maybe it tunneled into place. You step back from the whiteboard and realise you've drawn something truly awful. A particle with little arms climbing over a fence, complete with cartoon tunnel beneath labelled escape route. But hey, this is the quantum world. Logic left a long time ago. One last unsettling realisation before you call it a night. If particles can be somewhere they have no right to be, and if this behaviour is not rare, but constant and necessary to how the universe functions, then maybe everything you think of as impossible is just a matter of odds. And the universe? It plays the long game. You're starting to notice that the deeper you go into quantum mechanics, the less you feel like you're standing on solid ground. You are promised particles, predictability, equations that describe motion, force, mass. Instead, you've been served uncertainty, superposition, spooky action, and now particles that ghost their way through walls like shy phantoms at a masquerade ball. And tonight, the room gets even stranger, because now we're opening the curtains on the so-called emptiness of space, virtual particles and vacuum fluctuations. You glance at the vacuum chamber in the corner of the lab, pristine, sealed, airless. Inside, there's nothing. That's the whole point, right? Remove all the atoms, all the particles, all the fields, and you're left with pure emptiness. Except, no. Because quantum physics has one more trick up its sleeve. The vacuum isn't empty. Not really, not ever. You walk over, press your hand gently to the side of the chamber, and imagine what's going on inside. It looks still, sterile, dead. But according to quantum field theory, the vacuum is a roiling sea of activity, bubbling with so-called virtual particles that pop into and out of existence faster than any detector can catch. These aren't real particles, not quite. They can't be measured directly, and they don't leave tidy tracks in your instruments. But they're there. They affect measurable things. Their fingerprints are smeared across the fabric of reality itself. You sit back down and pull up your notes on vacuum energy. Every quantum field, electromagnetic, gravitational, whatever else we've dreamed up, is subject to fluctuations. Even in its lowest energy state, the field is not still. It twitches, it jitters, it vibrates with uncertainty. That's the root of these fluctuations. The Heisenberg uncertainty principle strikes again. You can't pin down both a field's value and its rate of change precisely, so even when you reduce the energy of the system as far as it'll go, you're left with residual motion. Tiny, chaotic, relentless. These fluctuations give rise to pairs of virtual particles, usually a particle and its corresponding antiparticle. They wink into existence, borrow a little energy from the vacuum, and then annihilate each other in a whisper before they violate any cosmic accounting laws. You raise an eyebrow. That's the deal. They can borrow energy, but only for a short time. Delta E times delta T approximately h bar over 2. The smaller the time, the bigger the temporary energy spike allowed, and these ghostly pop-ups matter. One of the most famous confirmations comes from something called the Casimir effect. You place two uncharged metal plates extremely close together, micrometers apart, and guess what? They move. They're pulled toward each other, not because of electromagnetism, not gravity, but because the virtual particles outside the plates outnumber the ones that can fit between them. The vacuum is exerting pressure, the vacuum is doing work. Historians still argue whether the Casimir effect should be explained strictly in terms of virtual particles or as a boundary condition on the quantum field. But either way, the math works, and the plates move. Empty space has structure, and energy, and potential. Which leads you to a disturbing and quirky implication. The vacuum isn't the lowest energy state. There could be false vacuums, metastable states that look like emptiness, but are actually trapped in a kind of energetic plateau. If the universe ever slipped from one of these to a true vacuum state, well, it would be bad. The laws of physics could change, particles could dissolve, time might behave differently. It's called vacuum decay, and while there's no evidence it's going to happen anytime soon, the math suggests it's technically possible. Somewhere out there, a bubble of better vacuum might be expanding at the speed of light, rewriting physics as it goes. If it reaches you, you wouldn't even know. No warning, no pain, just poof. Anyway, sweet dreams. You blink hard and turn your attention back to something more comforting, like electron self-energy. Even that is affected by virtual particles. In quantum electrodynamics, QED, the electron constantly emits and reabsorbs virtual photons. This affects its mass, its charge, everything. Your electron is not a lonely point in space. It's wrapped in a storm of virtual activity, constantly buzzing, constantly jittering. In fact, one of the greatest triumphs of quantum field theory is that it predicts the anomalous magnetic moment of the electron with ridiculous precision, matching experimental data to something like 13 decimal places. That agreement is only possible if you include virtual particles in the calculations, so you can't dismiss them as just theoretical. They shape real outcomes, even if you can't catch them red-handed. You spin slowly in your chair, eyes unfocused, and imagine what's happening in the empty space between your fingers. Pairs of virtual particles are being born and dying, all while you sit here pretending that nothing exists between you and the wall. You're surrounded by activity even in silence, even in stillness. One fringe theory even posits that everything, matter, forces, maybe even space-time itself, could be emergent phenomena from these quantum fluctuations. That the universe is not built from things, but from relationships between fluctuations. Like ripples on an ocean you'll never see, only feel. You shudder, just a little. The vacuum is not calm, it's loud, and it might be the real foundation of reality. And speaking of loud, remember Hawking radiation? The idea that black holes emit faint radiation over time. That too involves virtual particles. The concept goes like this. Near the event horizon, a pair of virtual particles appears. One falls into the black hole, the other escapes. But because one got trapped, the universe treats the escaping one as real, and the black hole loses a bit of mass. Black holes evaporating into nothing, because of the vacuum. That's quantum mechanics for you. Emptiness is full, silence is noise, and the void is never really void. You think back to the opening of your vacuum chamber. You thought you had created nothing, but in truth, you had unleashed a party no one could see. A churning ballet of fleeting somethings, borrowing, cancelling, pushing, pulling. And here's the final twist. Some physicists argue that this vacuum energy, the jittering of all these fields, is what's driving the accelerating expansion of the universe. Dark energy, that great cosmic mystery. Maybe it's not some exotic substance, maybe it's just the vacuum doing what it's always done. Buzzing, breathing, expanding, the smallest flickers, reshaping everything. So the next time you look into the darkness and think, there's nothing there, remember this, there's always something. Even in the void, the universe never truly stops whispering. The vacuum isn't empty. Time isn't linear. Particles don't stay put. You're beginning to think quantum mechanics isn't a scientific theory so much as an elaborate dare. And just when you thought things couldn't get any more reality bending, quantum physics casually tosses another paradox your way. Tonight's mind melter, delayed choice and the retroactive past. Yes, you read that right. Your present decisions might be reaching back in time to influence the past. You lean forward and pull up a file labelled simply, Wheeler's Delayed Choice Experiment. You remember it from earlier, vaguely unsettling, deeply confusing, time to look it in the eye. John Archibald Wheeler, physicist and occasional quantum trickster, proposed a variation on the double-slit experiment with a devious twist. What if you delayed your decision about how to measure the photon until after it had already passed through the slits? Seems impossible, right? Surely the photon must have already chosen its path, either slit A or slit B, before your measurement choice. But when you set up the experiment and choose to detect which path it took, the interference disappears, as expected. If you instead choose to observe an interference pattern, which only forms if the photon behaved like a wave and went through both slits, you get that too. Here's the catch. Your choice was made after the photon passed through the slits. It's as if the photon retroactively decided how to behave based on your later decision. You sit back and stare at the ceiling again. This has to be a trick. There's no way present measurements affect past events. That would tear causality apart, wouldn't it? Well, quantum mechanics politely clears its throat and says, define past. In the quantum world, until a measurement is made, a system's properties aren't fixed. Not hidden, not delayed, just not decided. The photon doesn't choose a path until it must, until the universe forces the issue through observation. So Wheeler's delayed choice tells you that the photon's past behavior isn't locked in until the present tells it what kind of story to write. It's like showing up to a bookstore, picking the mystery novel instead of the romance, and the last chapter rewrites itself accordingly. You find that deeply unsettling. Historians still argue whether Wheeler meant his thought experiment as literal time travel or as a philosophical metaphor about measurement. But modern experiments have taken it quite seriously, and the results hold up. The interference pattern disappears or persists depending on a later measurement, one that should have no possible influence on what already happened. You try to rationalize. Maybe the photon didn't really go through the slit yet. Maybe the whole experimental setup bends time in some odd way. Nope. They've done it with real-time random number generators to choose the measurement mode after the photon has passed the slits. Still works. There's even a version using cosmic light. Photons emitted billions of years ago from quasars, their measurement settings chosen by events that occurred long before Earth even formed. Same results. In a way, the universe seems to wait until all the context is available, before committing to a narrative. The past is provisional. It's like quantum mechanics has its own version of editing history, but only within the bounds of what can be known. You reach for your notes, hand a little shaky. There's something almost theological about it. A universe that doesn't simply exist, but one that waits to be asked the right question before settling on an answer. And the question shapes the past. One fringe idea, you saw it on a forum full of extremely sleep-deprived physicists, is that the universe doesn't have a single, fixed history. Instead, it has a consistent one. That is, all the events line up logically after the fact. But they weren't necessarily real before the whole structure was defined. Sort of like an improvisational play that only retroactively becomes a coherent story. You're reminded of the quantum eraser, a closely related experiment that takes things even further. In that setup, you can actually erase the which path information after the particle has hit the detector and the interference pattern comes back. It's as if the photon's earlier behavior remains in a kind of suspended uncertainty until all the relevant measurements are made. So now it's not just your future affecting the past, it's your memory of the future that rewrites the past. Let that one sink in. You blink slowly, reaching for your glass of water, which now feels suspiciously unstable. You glance at it like maybe it's going to spontaneously act like a wave and spread across the counter. Okay, probably not, but the implications of delayed choice are massive. It tells us that reality doesn't lock in frame by frame like a film reel. It waits, it listens, it collects all the data, all the observations, all the measurements, and only then decides what happened. Your idea of causality, the chain of A causes B causes C, might be true at the classical scale. But down here in the quantum realm, events influence each other in a network, not a line. It's more like a web with strands stretching in every direction. Tug one strand now, and the vibration ripples not just forward, but backward. One practical note: delayed choice doesn't violate causality in a way that would allow paradoxes. You can't use it to send information into the past. No quantum texting your past self-lottery numbers. The results are always random when viewed locally, but globally, in context, everything lines up. And that's the trick. The universe isn't contradicting itself, it's just holding off on the details until they're needed, a bit like a lazy writer who doesn't fill in the plot until the final chapter. So you ask yourself, what else isn't decided yet? What moments in your own past are still quantum fuzzy, waiting to be shaped by decisions you haven't made? Did that photon pass through slit A or slit B? Did you send that risky text or not? Did the universe lean left or right? Maybe the answer is yes, until you measure, until you know. And then the past settles into place, one quiet collapse at a time. You look around your lab, silent, dark, pulsing with fluorescent hums and the soft breathing of machines. You think of all the data, all the histories waiting to be collapsed, all the particles that are even now deciding how they behaved yesterday, based on what you choose to ask tomorrow. You never thought you'd end up negotiating with the past. But in the quantum world, the timeline is a collaboration, not a recording, a conversation. The lab is quiet again, as if even the machines are hesitant to hum too loudly after the realization you just had. Time might not be a one-way street. The universe might be playing it loose with the past, editing events not with ink and eraser, but with quantum suggestion. And now you're going to twist that knife a little further, because it's time to dive into the experiment that doesn't just rewrite the past, it unwrites it. Welcome to the quantum eraser, where particles seem to say, "Oops, never mind," after something already happened. You swivel in your chair and bring up the experiment on your screen. This one's a beast. Not because it's particularly violent, nothing in quantum physics is ever loud, but because of how elegantly it dismantles your last shred of classical comfort. Here's the basic setup. Take a classic double-slit experiment, but make it fancier. You fire photons one at a time through the slits. This time, however, you add a clever twist. You entangle each photon with a partner, call them twins, born from the same quantum event. Photon A goes through the slits and lands on a screen. Photon B, the twin, takes a detour toward another detector far away. Now, you might think, okay, whatever, it's just another entangled particle thing. But here's where it gets weird. You send photon A through the slits and it hits the screen. You get a scatter of dots, nothing new there. But the pattern those dots make, interference or no interference, depends on what you do with photon B afterward. Let me say that again, in case your brain skipped it out of self-preservation. What you choose to do with photon B after photon A hits the screen determines whether photon A behaves like a wave, interference pattern, or like a particle. Two clumps, no interference. Even though A is already done, already detected, already collapsed, supposedly. If you measure which path photon B took, you get a particle-like pattern from photon A. If you erase the which path information for photon B, by cleverly designing your detectors, you recover an interference pattern from photon A. After the fact, you rub your temples. Surely this is just a data sorting trick, right? A statistical illusion? But no, the experiments are real, repeatable, peer-reviewed. The patterns show up or vanish depending on whether the which path information exists, even if it was never actually recorded or read. The mere potential to know is enough to destroy interference, and the potential to unknow brings it back. You sit with that for a minute. Reality, it seems, is reversible at the quantum level, but not in a classical way. You can't go back and undo a measurement, but you can erase the context that would make it meaningful, and in doing so, you change how the past looked in the first place. It's not like saying, oh, that particle was a wave all along. It's more like the universe responds with, well, now that you've decided not to know, I guess it was a wave, and rearranges your results accordingly. Historians still argue whether the quantum eraser undermines the idea of objective history, or just forces us to rethink what events even are. Because in this case, the event, photon A landing on a screen, isn't fully real until the entangled twin is dealt with. You're starting to realize that measurement isn't a simple act of collecting data. It's a story you tell the universe, and if you change the story mid-sentence, the previous chapters rewrite themselves to stay consistent. Here's a fringe-flavoured philosophical angle. If all outcomes are entangled with each other, and our choices affect what counts as a history, then maybe there is no single objective timeline. Only collections of entangled events, braided together into consistent narratives. If you're not slightly nauseous yet, congratulations. You're probably lying. You look again at the results on your screen. Dot patterns. Waves where there should be particles. Particles where there should be waves. And all of it depending on knowledge, whether something could be known or was deliberately erased from existence. You can't help but think of memory. What else might be rewritable if knowledge itself is the key? Are there moments in your life, minor, fuzzy, unmeasured, that only feel solid because you haven't gone back and tried to observe them more closely? Is memory its own kind of quantum eraser? One mainstream defense against complete existential despair is that quantum erasers don't allow for communication with the past. You can't use the experiment to send a message backward in time. The results are only meaningful after the fact when all the data is correlated. It's like a riddle that only makes sense once the answer is already known. Still, the implications are uncomfortable. You picture the photon twin setup again. One photon flies toward a screen, its fate undecided. Its twin flies in another direction, toward a choice, to be measured or erased. The choice determines how the first photon behaved at the time, but that behavior doesn't exist in isolation. It's part of a larger tangled whole, and once again, the universe seems to be whispering, nothing is real until it fits the story. A quirky historical note. In some early versions of the quantum eraser, researchers used beam splitters to randomly decide whether to erase the witch path information. The results still matched. Erasure brought back interference, even when the system made the choice randomly. So it's not human will shaping the past, it's the presence or absence of distinguishability. If the universe can tell which path something took, even in theory, the interference vanishes. If that knowledge is erased, even after the fact, the pattern returns. It's not about conscious observation, it's about consistency. The past is like a book with rewritable ink, not because someone's lying, but because the final version depends on what the next page demands. You can't fake the data, but you can shift the framework around it and watch the events rearrange to comply. You lean forward and sketch 2 dots and 2 paths, a choice, an erasure, an outcome, and you wonder, for the 100th time, if the universe is less like a machine and more like a courtroom, where evidence matters, but only after it's been admitted into the record. One last thought before you shut down your monitors. The quantum eraser doesn't just say, what happened can change. It says that what happened never fully existed until it was entangled with what came next. Your memories, your choices, your observations. Each one might be collapsing a little cloud of possibility, not just in the future, but in the past. So you press your hand to the desk, feeling the wood grain beneath your fingertips. Solid, familiar, and yet, you can't help but ask, what part of the world is still waiting to decide what it already was? You've been walking through the quantum maze long enough to lose track of where you started. Particles don't stay put. Time can bend around your choices, and even nothing is filled with frantic, frothing activity. But tonight, the lights in the lab feel a little dimmer, the hum of the electronics a bit more distant, as if the room itself is waiting for you to notice something deeper, something quieter. Because now we're going to talk about a paradox so fundamental, it slips past most casual observers without setting off any alarms. Particles playing possum. That is, the unsettling idea that until a particle is measured, it's not really there at all. Not in the way we usually mean. Not hiding, not pretending, just not existing in a specific location. Like a Schrödinger's cat who forgot to wake up and stayed in the maybe state a bit too long. You've seen the word already. Superposition. But it's easy to forget what it really implies when you get used to the math. It's not that a particle is in both places at once, and it's not flitting rapidly between 2 options like a hummingbird with commitment issues. It's more bizarre than that. The particle genuinely has no defined position. It doesn't even possess the property of where in any meaningful way. It has a probability distribution, a range of possibilities, a wave function that tells you where it might show up but gives you no guarantees. You sigh and glance at your desk, that pencil. It's not quantum, it's where you left it. But if that pencil were an electron and you hadn't yet observed it, you'd be forced to admit it could be anywhere, or nowhere, or both. You walk over to the old double-slit setup, still resting quietly on its workbench like a loaded philosophical weapon. You fire a photon, just one. You don't know which slit it goes through. You don't even know if it went through the slits in any traditional sense, but the interference pattern says it was aware of both slits. Aware. That's a dangerous word in quantum physics. Makes it sound like the particle was making choices, but really it was playing possum, refusing to take on classical attributes like position until someone demanded it. Historians still argue whether this means the particle lacks definite properties before measurement, or whether those properties exist in some hidden form, just inaccessible to us. This is the heart of the realism debate. Is the world there when we're not looking, or does it only come into being when we engage with it? Einstein, never one to let things go gently, hated the idea of an incomplete reality. "I like to think the moon is there even if I'm not looking at it," he once quipped. But the quantum world doesn't offer that kind of reassurance. The moon might be there, but it might also be in a spatial superposition the size of a galaxy. And we'll never know unless we measure. There's a related idea known as quantum contextuality, which basically says that the outcome of a measurement can depend on what other measurements are being made at the same time. So not only does the particle play possum, it adapts its performance to the rest of the experiment. It's like asking someone their favourite movie, and their answer changes depending on whether you also ask them about snacks or weather. The context shapes the content. One fringe interpretation you may have stumbled across is the cubism school of thought, where quantum probabilities aren't about objective properties at all. They're just tools for updating your beliefs. The wave function isn't the particle, it's you, your knowledge, your perspective, your limited view of something too strange to pin down. But let's bring it back to the lab. You fire another photon, it vanishes into the apparatus. You don't know where it is now, you can't know, not until it shows up on the screen. And when it does, it doesn't leave a trail. It doesn't say, hey, just came through slit A by the way. No breadcrumbs, no track marks. It just appears. And it's only after a long chain of these appearances that the pattern begins to take shape. A map of probabilities. A ghostly portrait of what the wave function suggested might happen. And the more you watch, the more your classical intuition unravels. Because if a particle doesn't have a location until measured, then it's not really there at all. Not like a marble in a sock drawer. It's a set of possibilities that sometimes, under the right conditions, resolve into a single outcome. Like the world is drawing cards from a deck one photon at a time, and before the draw, the card doesn't even exist yet. You sit with that thought, letting it curl around your spine. Maybe that's what existence is, at the quantum level. Not a permanent thing, but a potential thing. A waiting to be thing. One quirky fact. This isn't limited to photons or electrons. Even large molecules, dozens, hundreds of atoms, can exhibit the same behaviour. Their wave functions can spread out, interfere, play possum, until something looks, until reality taps them on the shoulder. Even more startling, some researchers are exploring whether biological systems, proteins, enzymes, even parts of the brain, might exploit quantum indeterminacy. Your neurons, your thoughts, they might occasionally dip their toes into the fuzzy maybe-verse before popping into focus. You chuckle softly. Brains in superposition. Sounds like a failed rock band. But here's the real bite. This quantum behaviour isn't going away. It's not a mistake. It's not a fluke. It's foundational. Particles aren't waiting to be found. They're not hiding under the bed. They're not pretending. They're just undefined. Not because they're lazy, because that's how the universe is built. When no one asks the question, the answer doesn't exist. And when someone finally does, the answer arrives, but only one of them, and you'll never know what the others might have been. You stare at the screen again, at that single dot, alone in a field of maybes. Not because it was always there, but because you finally looked. You're starting to feel like a detective in a mystery novel that forgot to include a solution. Every time you uncover a new clue about the quantum world, it just raises more questions, and somewhere in the fog of probabilities you're not even sure there is a culprit. But you're not alone in this. Tonight you step into the middle of a decades-long argument between two of the sharpest minds physics has ever known. Bohr versus Einstein. Whose beard wins? This isn't just an academic spat. It's the central philosophical cage match of quantum mechanics. And unlike most scholarly debates, this one involved real shade, subtle jabs, and some pretty dramatic thought experiments. Let's set the scene. It's the 1920s. Classical physics is on the ropes. Quantum mechanics is exploding onto the scene with a flurry of new ideas. Wave functions, uncertainty, superposition. A young, mathematically gifted crowd is embracing it all with terrifying enthusiasm. And then there's Niels Bohr, philosopher-physicist extraordinaire, champion of the Copenhagen interpretation. Bohr believed that quantum systems don't have definite properties until measured, that the act of observation isn't passive, it's participatory. In his view, quantum mechanics doesn't describe objective reality, it describes our knowledge of reality. The math doesn't tell you what is, it tells you what you can expect to observe. To Bohr, this wasn't a bug, it was the beauty of the theory. Then there was Albert Einstein, theoretical heavyweight, godfather of relativity, and reluctant guest at the quantum party. Einstein had serious doubts, not about the equations, they worked, no one denied that, but about what the theory meant. He couldn't accept a universe that was inherently probabilistic, a place where particles didn't have properties until someone came along and poked them. His famous objection? God does not play dice with the universe. Bohr's reply? Stop telling God what to do. Cue the slow clap, you sip your tea and shake your head. Imagine being smart enough to throw theological shade in a physics debate. The back and forth played out over years, mostly through letters, conferences, and increasingly elaborate thought experiments. Einstein kept trying to expose hidden flaws in Bohr's interpretation, some missing piece that would restore order, determinism, and sanity. He was convinced that quantum mechanics was incomplete, that the randomness in measurement wasn't real randomness, just the result of hidden variables, details we couldn't see yet. So he came up with thought experiments to challenge Bohr's view. One of the most famous, the EPR paradox. Published in 1935 by Einstein, Podolsky, and Rosen, the paper posed a simple but devastating question. If two particles are entangled and you measure one, the other's state becomes instantly known no matter how far apart they are. That's faster than light. That's non-locality. That's wrong, right? EPR argued that this implied one of two things. 1. Quantum mechanics is incomplete. It's missing hidden variables that would make the outcomes deterministic. Or 2. The universe allows spooky action at a distance, which violates relativity. Bohr, of course, had an answer, a frustrating one depending on how much you value clarity. He said that the measurement on one particle doesn't send information to the other, it just completes the definition of the system. The entangled pair is a single quantum object. Measuring one doesn't affect the other, it just reveals the correlation that already existed in a non-classical, non-local way. Einstein predictably was not impressed. Historians still argue whether Bohr was being deep or just evasive. His writing was notoriously dense. Some called it philosophical fog, but it's possible he saw something others didn't. A way to keep quantum mechanics consistent without clinging to the old comforts of determinism. The debate remained unresolved for decades. Both men took their positions to their graves, never conceding. Bohr defended complementarity, Einstein demanded realism. And then, in the 1960s, a new player entered the ring, John Bell. Bell did what Einstein and Bohr never could. He translated the debate into something testable. He derived an inequality, Bell's inequality, that could distinguish between local hidden variable theories and quantum mechanics. If nature obeyed local realism, Einstein's hope, the inequality would hold. If quantum mechanics was correct, the inequality would be violated. Spoiler, it was violated, repeatedly, decisively, over decades. Experiments by Aspect, Schrödinger, and others closed loopholes and confirmed what the math had predicted. The universe is not locally deterministic. Either it's non-local, or it fundamentally lacks hidden variables. Bohr's view, frustrating though it was, had more support. But Einstein wasn't entirely wrong. His instincts that quantum mechanics might be incomplete have continued to echo through modern physics. String theory, quantum gravity, loop quantum cosmology all attempt to go beyond standard quantum theory, maybe not to restore determinism, but to unify the whole mess into something more coherent. And Bohr? His refusal to define an objective quantum reality has aged into what some call epistemic humility. A reminder that just because our measurements yield answers doesn't mean the universe works like we expect. You lean back and smile at the thought. Two giants, neither fully victorious, both essential. Their legacy is more than equations or theories. It's the realization that how we ask questions shapes the universe we uncover. A quirky historical footnote. At the 1927 Solvay conference, the who's who of physics gathered in a now iconic photo. Einstein and Bohr sit just rows apart. Behind them, Schrödinger, Dirac, Heisenberg, Pauli. It looks like a class reunion for gods. But what most people forget? Einstein reportedly skipped some of the lectures. Not out of arrogance, he just couldn't stand the interpretations being presented. And Bohr? He spent entire evenings pacing the hotel lobby, muttering through rebuttals, crafting responses to Einstein's objections long after the sessions ended. This wasn't just a science debate, it was a battle over the soul of reality. And you? You're standing right in the middle of it, still unsure which beard wins, still trying to find your footing in a world where truth might depend on when and how you choose to ask. Maybe Bohr was right. Maybe Einstein was too. Maybe the only mistake is thinking there's one answer. You're not even surprised anymore. The moment your eyes meet the blinking interface on your workstation, the one quietly running a simulation of quantum interactions near black holes, you know it's time to let go of whatever scraps of reality you are still clutching. Because if there's one place in the universe that throws every law, theory, and shred of common sense into the singularity, it's the black hole. And you, dear traveller, are about to witness what happens when quantum mechanics and gravity meet in a back alley and throw down. Welcome to the intersection of space-time and madness. Tonight's topic, black holes and particle poker. Let's start simple, relatively speaking. A black hole forms when a massive star collapses under its own gravity, compressing matter into a point of infinite density, the singularity. Around that, there's the event horizon, a boundary so absolute that not even light can escape once it crosses. At first glance, it looks like classical physics might be enough here. Gravity, mass, curvature of space-time, Einstein's wheelhouse. But if you start asking quantum-level questions about what happens at and inside the event horizon, the math screams back in protest. The first sign of quantum weirdness in black holes came from someone you might have heard of, Stephen Hawking. In the 1970s, Hawking decided to apply quantum field theory to the curved space-time near the event horizon. And what he discovered was shocking. Black holes aren't entirely black. They emit radiation. We now call it Hawking radiation, and it arises from, you guessed it, vacuum fluctuations. You remember those from earlier? Even in empty space, virtual particle pairs are constantly appearing and annihilating. Near the event horizon, something stranger happens. If a pair forms right at the edge, one particle might fall in, while the other escapes. The one that escapes becomes real, visible as radiation, and to preserve energy balance, the black hole loses a tiny bit of mass, which means black holes evaporate, slowly, painfully, over trillions of years. At first, physicists were thrilled. Quantum mechanics had brought something new and testable to black hole physics, and then the information paradox showed up to ruin the party. Here's the problem. When something falls into a black hole, its information, the arrangement of particles, quantum states, all that delicious detail, should be preserved. That's one of quantum mechanics' golden rules. Information can't be destroyed. You can scramble it, sure, but it's never gone. But Hawking radiation is thermal, featureless. It doesn't carry any information about what fell in. So if a black hole evaporates completely and all we're left with is generic radiation, then the information is gone. Poof. That violates quantum mechanics in the most fundamental way. It's like playing poker, and the dealer eats your cards after every hand, claiming, "Don't worry, the system is still fair." You'd flip the table, and physicists did. The black hole information paradox became one of the most important unsolved problems in theoretical physics. Hawking himself originally accepted that information might truly be lost. He later changed his mind, but the damage was done. Theoretical papers multiplied like entangled particles at a rave. Historians still argue whether the original formulation of the paradox was overblown, or if it revealed something fundamentally flawed in how we understand space-time and quantum mechanics together. Spoiler, it's probably the latter. You take a deep breath and think about what it means for the universe if information can be destroyed. That every choice, every bit of structure, every fingerprint of what fell into a black hole might simply vanish. Or maybe not. Enter the holographic principle. This idea, developed by Gerard T. Hooft and later expanded by Leonard Susskind, suggests that all the information contained in a volume of space can actually be described by data encoded on its boundary. That's right. The information of a 3D object might be stored on a 2D surface, like a hologram. And guess what? The entropy of a black hole, how much information it can contain, scales not with its volume, but with the area of its event horizon. The math checks out. The metaphor is wild. You're sitting here, thinking about everything you've ever known, and now someone's telling you it might all just be a projection, and that black holes aren't information shredders, they're storage devices. Quantum physicists and string theorists jumped on this. If information is preserved on the event horizon, maybe Hawking radiation isn't truly random. Maybe it contains subtle correlations. Maybe it encodes the history of what fell in. But if that's true, how do we get that information back? Enter black hole complementarity, a proposal that says both viewpoints, information falling into the black hole and being encoded at the boundary, can be true depending on your frame of reference. From the outside, the infalling matter appears to smear across the event horizon. From the inside, it falls smoothly toward the singularity, and no observer can see both views at once. You chuckle. Of course they can't. This is just classic quantum mechanics now painted on a cosmic scale. Then there's firewall theory, a newer proposal that tries to resolve the paradox by saying, fine, maybe the event horizon isn't smooth. Maybe it's a wall of high-energy radiation that burns anything that tries to cross. A brutal solution, a sacrifice of general relativity's cherished principle that falling into a black hole should feel, well, boring. But no one likes that answer, because it means that even the smoothness of space-time breaks down at the quantum edge. The truth is, we still don't know. Quantum gravity, the unifying theory of quantum mechanics and general relativity, doesn't exist yet. Not fully. String theory has candidates. Loop quantum gravity has candidates. But no one's won the tournament yet. You stare at your simulation again. A virtual black hole spins lazily, shedding a trickle of digital Hawking radiation. Somewhere in that cascade, according to some theories, are the quantum ghosts of every particle that ever fell in. Encoded, encrypted, waiting to be decoded. One final quirky tidbit for the night. Hawking once bet that information was not preserved, and later conceded the bet. The prize? A baseball encyclopedia. Because even in theoretical physics, you need stakes. You imagine falling into a black hole, watching the stars stretch and smear across your field of view, time slowing, space twisting. And as you cross the horizon, you wonder, will someone someday read your story in the pattern of radiation left behind? Will the universe remember you? Or will it play one last poker hand and fold? You're starting to feel like reality is less a well-built house and more an enormous pile of blankets, layered, tangled, and weirdly warm. But if you pull on the wrong corner, the whole thing collapses. But tonight you're going to pull on one of those corners anyway, because now we arrive at the strange humming world of quantum computers, where information isn't stored in bits and bytes, but in ghostly, overlapping states that somehow do math before they even decide what numbers they're working with. Welcome to the age of computation by uncertainty. Tonight's dive, building quantum computers with schizophrenic bits. You take a moment to appreciate how far we've come. Classical computers, the one you're using right now, run on bits. A bit is either a 0 or a 1. That's it. The entire internet, every meme, every song, every email chain from 2009 you've never deleted. Just long strings of zeros and ones. It's fast. It's powerful. It got us to the moon and brought you cat videos. But there are problems classical computers struggle with. Problems where even the best silicon starts to sweat. Like factoring enormous prime numbers, or modeling the quantum behavior of molecules, or searching unsorted databases with terrifying efficiency. Enter the qubit, the quantum bit. Unlike a classical bit which has to be 0 or 1, a qubit can be in a superposition of both at once, until measured. Just like the particles you've been chasing through the last 18 sections. You stare at the image of a spinning sphere on your screen. That's the Bloch sphere, the geometric visualization of a qubit. It's not just flipping between 0 and 1 like a coin, it's spinning through every possible combination of those two states, simultaneously. So when you build a quantum computer, you're not just adding more bits, you're exponentially expanding the number of states your system can hold. 1 qubit equals 2 states, 2 qubits equals 4 states, 3 qubits equals 8 states, and so on. By the time you get to 300 qubits, theoretically, your quantum computer is processing more possible states simultaneously than there are atoms in the observable universe. Let that one marinate. But before you get too excited and start building one out of coat hangers and leftover coffee filters, understand this. Quantum computers are wildly temperamental. They require incredible control, near absolute zero temperatures, precise entanglement, and heroic levels of error correction. Because remember, qubits are fragile. They decohere like dropped Jenga towers. The tiniest interaction with the environment, heat, light, cosmic rays, your ex texting you, can collapse their delicate superpositions and ruin the entire calculation.
Yeah.
And unlike classical bits, you can't just look at a qubit mid-computation to see how it's doing. Because the moment you measure it, the wave function collapses. You don't see what it was doing, you only see one possible outcome. That's why quantum algorithms have to be designed with ninja-level subtlety. The goal isn't to find an answer directly, it's to manipulate the quantum system so that the right answer becomes the most probable one when you measure. It's not about knowing, it's about steering uncertainty until the universe coughs up a result. It's poker again, but this time you're playing against probability itself. You've probably heard of Shor's algorithm, the quantum code that can factor large numbers exponentially faster than any classical algorithm. This terrified governments and delighted mathematicians because large number factoring is the foundation of modern encryption. If quantum computers get powerful enough, they could break RSA encryption like it's made of graham crackers. And then there's Grover's algorithm, which allows you to search an unsorted database in roughly square root of n time instead of n. Sounds boring. Imagine cracking a password in half the time without even knowing how you guessed. These aren't faster computers, they're different computers. They don't process data sequentially. They don't check one possibility after another. They explore all possibilities at once, guided by interference and entanglement, pruning the wrong paths, amplifying the right ones. It's a dance of maybes that somehow collapses into a useful answer. Historians still argue whether quantum computing will scale to practical levels in our lifetime, or remain forever in the land of small prototypes and massive funding proposals. As of now, the biggest quantum processors boast a few dozen to a few hundred qubits, depending on how you define usable. Companies like IBM, Google, and startups with way too cool names are racing to scale up, overcome decoherence, and build fault-tolerant architectures. And then there's the question of what else quantum computing can do. Could it simulate quantum systems that are otherwise impossible to model? Could it unlock new materials, medicines, or insights into fundamental physics? Could it, given enough clever algorithms, simulate you? Some researchers quietly speculate that consciousness itself might be a kind of quantum computation, though this remains deep in fringe territory. Don't bring it up at a conference unless you enjoy awkward silence and polite smiles. But here's a quirky twist. Some parts of quantum computers behave less like machines and more like oracles. You don't watch them think. You ask them something, and they give you an answer, with no real insight into how they reached it. Kind of like a very expensive, very cold magic 8-ball. And sometimes the answers are so probabilistic that you have to ask the question multiple times, just to get a distribution you can trust. This isn't a defect, it's quantum computing in action. It's a world where certainty is engineered, not assumed. Where reality isn't read, but negotiated through interference patterns and gentle nudges in Hilbert space. You sketch a qubit on your notepad. It looks like a sad pancake. You label it Barry. Barry exists in a superposition of doing everything and doing nothing, which honestly feels a little too relatable right now. But there's a final thought that catches your breath. Quantum computers don't just challenge how we compute, they challenge what it means to know. If you can't observe your data mid-process, if you can't reverse engineer the solution path, if all you ever get is a collapse and a probability, then your answers aren't just outputs, they're collaborations with uncertainty. And maybe that's not so different from how the rest of the universe works. Maybe your thoughts, your memories, your decisions, they're all quantum processes, decohered just enough to feel stable. Maybe you're made of bits too, not zeros and ones, but Barry-level maybes. You've now walked through the deepest corridors of the quantum world, somewhere between a dream, a glitch, and a perfectly calibrated probability engine. You've faced particles that vanish, timelines that rearrange themselves, and wave functions that seem to wink at your expectations. So there's only one question left, the biggest one, the one that quietly haunts the background of everything you've seen so far. Do you collapse the universe just by watching? You probably already know where this is going. From the double-slit experiment to quantum erasers and delayed choice scenarios, everything seems to come down to the observer. Not in the classical sense of someone holding a clipboard and a cup of coffee, but in the quantum sense of a system being forced to pick a side, collapse a wave function, and stop being fuzzy. But what is an observer? You stare at your hand. It's made of atoms, electrons, quarks, just like the particles in your experiments. So how does something as wavy and undefined as a particle give rise to something so stable? And more urgently, does your act of noticing a particle change what it is? The traditional Copenhagen interpretation would say, yes, the act of observation collapses the wave function into a specific state. Until then, it was just a cloud of probabilities. But what counts as observation? Is it a person looking at the particle, a sensor, a photon, a spreadsheet, or something deeper, consciousness itself? This is where things get squishy and controversial, and let's be honest, deliciously fringe. Because while most physicists will warn you away from tying quantum mechanics to consciousness, the idea is hard to ignore. After all, the equations don't specify when a wave function collapses, only that it collapses when a measurement is made. But what defines a measurement? Some thinkers, like John von Neumann and Eugene Wigner, wondered whether it was mind that did the collapsing, that a conscious observer was required to turn a superposition into a single outcome, that before observation reality is undecided, and only when a mind enters the equation does it make a choice. This is known as the consciousness causes collapse theory. You blink slowly, you've been collapsing wave functions all night just by thinking about them. Wigner even devised a variation of Schrödinger's cat called Wigner's friend, where the observer inside the lab sees a definite outcome, but someone outside the lab still considers the whole system in superposition. Two observers, two realities, both consistent, but not reconcilable until they compare notes. So, is there one true outcome, or does each observer get their own? You sip water and try to not feel like you're about to split into 12 versions of yourself, just for having that thought. Now, most mainstream physicists reject the idea that human consciousness is necessary for measurement. They argue it's not awareness that matters, it's irreversibility. Once a system interacts with the environment in a way that leaves a permanent record, the wave function is effectively collapsed. That record could be anything: a scorch mark on a detector, a flip in a memory bit, a photon bouncing into a camera sensor. Consciousness, they say, is unnecessary. It's just along for the ride. But if that's true, why does it feel like the quantum world keeps dodging our expectations until we decide to look? Why does observation seem so intimately tied to existence? Maybe it's just anthropic bias. After all, you're here because the world behaves in a way that allows for beings like you to emerge. Of course, your perspective is tailored to experience classical certainty, not quantum chaos. But you can't shake the feeling that your participation matters. You're not separate from the system. You're a quantum object observing quantum objects. You're made of particles that once floated in overlapping possibilities and only became you after a billion collapsing wave functions carved you into coherence. Your thoughts, your feelings, your sleep-deprived hunger for one last slice of pizza, these all emerged from systems that evolved probabilistically. And now here you are asking the universe a question it refuses to answer directly. Do you collapse the universe just by watching? One fringe theory, known as participatory anthropic principle, proposed by John Wheeler, yes, the delayed choice guy, suggests that observers are necessary for the universe to come into being, that the universe exists because it knows it is being observed. Wheeler imagined the cosmos as a kind of self-creating feedback loop, quantum measurements made by conscious beings helping define the history of the universe retroactively. You raise an eyebrow. It's poetic, if nothing else, but it's also terrifying. If that's true, then maybe the universe is more like a question than a machine. And maybe your mind isn't just in the universe, but of the universe, co-creating its form with every choice, every glance, every question asked aloud. Even now, even here, you look down at your notes. You've got arrows pointing in opposite directions, diagrams that loop back into themselves, sentences that end with question marks next to exclamation marks, as if your pen couldn't decide how it felt about anything anymore. But somewhere beneath it all is a thread, a quantum thread. The idea that reality is not a list of things, but a web of relationships, entangled, uncertain, and ever collapsing into the moment. And you are part of it. So no, you don't collapse the universe, not all of it. But maybe, just maybe, you collapse your slice of it. Every time you look, every time you choose, every time you wonder, reality sharpens into form, one outcome, one path, one version of you walking forward, and all the other possibilities still waving just out of reach. The air in the lab is calm now, humming with gentle stillness. The equations have quieted, the particles have paused their endless dance, and your mind, once spiraling through timelines and tangled interpretations, has finally begun to settle. Let it all soften. Let the sharpness of paradox blur into curiosity. Let the quantum riddles melt into the same hush that lives behind silence. The screen in front of you dims, no longer a portal to uncertainty, but a mirror of your own quiet breath, steady and real. You've traced the paths of photons and electrons, walked the edges of black holes, peeked behind the veil of time. You've asked questions without answers, and that's okay. Not everything needs to be solved tonight. Some things can be held gently. Maybe the world isn't a puzzle to crack, but a whisper to hear. A presence that responds not to control, but to attention. You give it yours, and in return it offers a moment like this. So now, wherever you are, under covers, under stars, beside a softly humming fan, feel the edge of your awareness begin to dissolve. Let your thoughts drift into superposition. Let the weight of your body anchor you to this universe, this version of you, just as you are. The rest can wait. The questions will still be here tomorrow.